Hello friends, good evening. Today I plan to read out an article from Quanta magazine on popular maths. It's a pure math topic named as Pell equation. Ever since Archimedes, mathematicians have been fascinated by the equations that involve a difference between squares. Now, two mathematicians have proven how often these equations have solutions in concluding a decades-old quest. So the article is by Jordana Kapilevich and it is dated August 10, 2022. In the 3rd century BCE, Archimedes posed a riddle about herding cattle that he claimed only a few truly wise persons could solve. His problem ultimately boiled down to an equation that involves the difference between two square terms, which can be written as x square minus dy square equal to 1. Here d is an integer, a positive or negative counting number, and Archimedes was looking for solutions where both x and y are integers as well. So this is the Pell equation, x square minus dy square equal to 1. It's a Diophantine equation. We are looking for integer solutions for x and y. This class of equations called Pell equations has fascinated mathematicians over millennium since. Some centuries after Archimedes, the Indian mathematician Brahmagupta and later mathematician Bhaskara too provided algorithms to find solutions to these equations. In the middle of 1600s, the French mathematician Pierre de Fermat, who was unaware of that word, rediscovered that in some cases, even when d was assigned a relatively small value, the smallest possible integer solutions for x and y could be massive. When he sent a series of challenge problems to rival mathematicians, they included the equation x square minus 61 y square equal to 1. Whose smallest solution have 9 or 10 digits. As for Archimedes, his riddle essentially asked for integer solutions to the equation x square minus 4,729,494 y square equal to 1. To print out the smallest solution, it takes 50 pages, says Peter Koymans, a mathematician at the University of Michigan. In some sense, it's a gigantic troll by mathematics. So mathematicians love to play with large numbers. But the solutions to Pell equations can do much more. For instance, say you want to approximate root to an irrational number as a ratio of integers. It turns out that solving the Pell equation x square minus 2y square equal to 1 can help you do that. Root 2 or generally root d can be approximated well by rewriting the solution as a fraction of the form x by y. Perhaps even more intriguing, those solutions also tell you something about the particular number systems, which mathematicians call rings. In such a number system, a mathematician adjoins root 2 to the integers a plus b root 2, where a and b are integers. So you consider these numbers. Rings have certain properties and mathematicians want to understand those properties. The Pell equation, it turns out, can help them do so. And so a lot of very famous mathematicians, almost every mathematician in some period of time actually studied this equation because of how simple it is, said Mark Schusterman, a mathematician at Harvard University. Those mathematicians included Fermat, Euler, Lagrange, and Dirichlet. John Pell, not so much. The equation was mistakenly named after him. Though we know this equation as the Pell's equation, but Pell do not have much contribution in this area. Now, Koymans and Carlo Pagano, a mathematician at Concordia University in Montreal, have proved a decades-old conjecture related to the Pell equation, one that quantifies how often a certain form of equation has integer solutions. To do so, they imported ideas from another field, group theory, which simultaneously gaining a better understanding of key but mysterious objects of study in the field. They used really deep and beautiful ideas, said Andrew Grainville, a mathematician at the University of Montreal. They really nailed it. Broken arithmetic. In early 1990s, Peter Stevenhagen, a mathematician at Leiden University at Netherlands, was inspired by some of the connections he saw between Pell equation and group theory to make a conjecture about how often these equations have integer solutions. But I didn't expect it to be proved anytime soon, he said, or even in his lifetime. Available techniques did not seem strong enough to attack the problem. His conjecture depends on the particular feature of the rings. In the rings of the numbers where, for example, root over minus 5 has been added to integers, mathematicians often work with imaginary numbers like root over minus 5. There are two distinct ways to split a number in which into its prime factors. The number 6, for example, can be written not just as 2 into 3 but also as 1 plus root over minus 5 into 1 minus root over minus 5. As a result, in this ring, unique prime factorization, a central tenet of arithmetic, one particularly taken for granted in normal integers, breaks down. The extent to which this occurs is encoded in an object associated to the ring called a class group. So the concept of class group came in. One way that mathematicians try to gain deeper insights into a number system they are interested in, say root over 2 adjoint to the integers, is to compute the study its class group. Yet it is almost prohibitively difficult to pin down general rules for how class groups behave across all these different number systems. Peter Koymans in the library of Mathematical Institute of Leiden University, where he is a guest for the summer. So this is the picture of Peter Koyman. In 1980s, the mathematician Henry Cohen and Henrik Lenstra put forth a broad set of conjectures about what those rules should look like. These Cohen-Lenstra heuristics could tell you much about the class groups, which in turn should reveal properties of the underlying number systems. There was just one problem. While a lot of computations seem to support the Cohen-Lenstra heuristics, they are still conjectures, not proofs. As far as the theorem go, until very recently we knew almost nothing, said Alex Bartel, a mathematician at the University of Glasgow. Intriguingly, a class group's typical behavior is inextricably intertwined with the behavior of Pell equation. Understanding one problem helps make sense of the other. So much so that Stephen Hagen conjectures has also been a test problem for whatever progress has been made on the Cohen-Lenstra heuristics, Pagano said. The new work involves the negative Pell equation, where x square minus d square is said to equal minus 1 instead of 1. So the negative Pell equation says x square minus dy square equal to minus 1. In the contrast to original Pell equation, which always has infinite number of integer solutions for any d, not all values of d in the negative Pell equation yield an equation that can be solved. Take x square minus 3y square equal to minus 1. No matter how far along the number line you look, you never find a solution, even though x square minus 3y square equal to 1 has infinitely many solutions. So negative Pell equation is a special class among the Pell equation. In fact, there are a lot of values of d for which the negative Pell equation can be solved based on known rules about how certain numbers relate to one another. D cannot be multiple of 3, 7, 11, 15 and so on. But even when you avoid those values of d and consider only remaining negative Pell equation, it is still not always possible to find solutions in smaller set possible values of d where what proportion actually works. So that is the question. In case of negative Pell equation, for a given d, for what proportion of d we get solution. In 1993, Stephen Hagen proposed a formula that gave a precise answer to that question of the values for d that might work, that is, the values that are not multiple of 3, 7, etc. He predicted that approximately 58% would give rise to negative Pell equations with integer solutions. So this 58% is the discovery. Stephen Hagen's guess was motivated in particular by the link between the negative Pell equation and Cohen-Lenstra heuristics on the class groups, a link that Koyman and Pagano exploited when 30 years later they finally proved them correct. There are some more discussions in this line with some deep mathematics, but I am not going into it. I'll stop here. Thank you.